Hello, everybody. Welcome to the PyData DC Meetup. Today we have Brendan Collins join us, and he's going to be talking about Xarray-Spatial. Thank you to all of our sponsors, MetroStar Systems, Spell, Capital One, NVIDIA, and NumFocus. I am Hussein Sultan, by the way. Any announcements from our partners? I know, Stephanie, you have one.
Sorry, everyone, trying to be able to hit the unmute button. But yeah, so MetroStar is actually hosting an International Women's Day panel. This event is going to be completely virtual. It's going to be held this upcoming Monday on March 8th from 12 to 1 p.m. Eastern Time. So as you can see, the panel features a bunch of women and leaders from industry and government. So the panelists will be discussing a variety of topics, some including their journeys as women in technology and helping inspire other women leaders in technology. So we strongly encourage you all to attend this event, share it with your network. Your support would be greatly appreciated, and I will send the link in the chat so you all can take a look, learn more about the event, and RSVP if you're interested. So that's it from the MetroStar side. Thanks, Hussein.
Thank you, Stephanie. That is awesome. I'm looking forward to the panel. Any other announcements from our partners?
Just like I said a minute ago, Rapids is working on Colab again, so you can quickly use and install that. And we did just release version 0.18 with all sorts of fun improvements and great capabilities. So download and have some fun.
Awesome, thank you. If no other announcements, I am going to pass on the screen share to Brendan Collins. Brendan and I go way back. Brendan has just spent a immaculate career in GIS, and he is building out Xarray-Spatial. I am very excited to learn more about it, and Brendan, take it away. Before that, I have to say there's a code of conduct. Please be nice to everybody. Thank you.
Great. Thanks, Hussein. I'm going to take the screen share now with this continue button. I'm going to share my desktop. Are folks seeing a MakePath homepage right now? I'm going to minimize everyone's beautiful faces here. Are folks able to see my screen?
Yep.
Great, great.
Good night, everyone.
So yeah, thanks Hussein, and thanks to the PyData DC group for hosting me. My name is Brendan Collins. I'm the founder at MakePath, along with my co-founder Pablo Fuentes, and we focus on open source and geo, as you may imagine, and we try to find funding mechanisms for geo and also take open source tools to help solve client problems. You can visit us at makepath.com, and that's about the shameless plug that I'm going to do here. But the topic that I wanted to cover today was Xarray-Spatial. A little bit more about myself and my contributions to open source. So a big part of my focus is Xarray-Spatial that I'm covering today. But then I'm also a core developer on DataShader. So I got to be there during the first days of DataShader in 2015, 2016. Also a core contributor of Bokeh and creator of the King JSON Bible. So if you guys want to do NLP on the Bible, you could check out King JSON Bible here. But today I wanted to focus on Xarray-Spatial. And Xarray-Spatial is a Python-based analysis library for geo, specifically focused on raster-based spatial analytics. And we have a new Xarray-Spatial webpage. This is xarrayspatial.org, where you can come and read a little bit more high level about the library. But as an introduction, so when we were building DataShader, I was always the influence for geo, and I always wanted to add new geo functionality to DataShader. But other folks in the community, saw that there really warranted a separate project for geo-specific universal functions. So when we think about just the name Xarray-Spatial, obviously it starts with Xarray. So all of the functions inside of Xarray-Spatial will accept Xarray objects as input, in most cases, Xarray data arrays. And what you're going to get back from those analysis functions really boils down to a series of regular grid analysis functions. So we're working with rasters here. We can consider them arrays, vectors, or tensors, but in the geo world, we call them rasters. And Xarray-Spatial is a very flat library of utility functions. So what you're able to do is use many of the raster analytics that folks in the GIS world are accustomed to, things like image classification, and these are 1D classification methods, focal analyses where we're looking at the area around a specific pixel, things like convolution filters fall into this category, multispectral tools. These are element-wise calculations across things like Landsat bands. And one of the most classic multispectral analyses is NDVI. And folks may not be familiar with the history of NDVI, but NDVI was actually invented by Kodak. It was invented all analog because this was back in the 40s when they created NDVI. It was specifically created and funded by the US military to look at German bunker locations for D-Day. That's where NDVI comes from, is trying to figure out what parts of an image are alive and which parts aren't. So it's specifically finding vegetation. Since then, there's been a slew of other multispectral analyses that you can do. These are classic band math between different spectral bands inside of satellite imagery, all element-wise, so fairly easy to implement. Pathfinding, proximity, surface analysis, zonal analysis. We're going to be looking at these deeper, but these is the core of Xarray-Spatial, our utility functions, which apply to Xarray data arrays. And in this table, in these tables, you may notice that we have a couple of different array backends for these analyses, and we're working to build out all of the different use cases. So the classic one would be an Xarray data array that's backed by a NumPy array. So what Xarray is doing in this case is that it's adding labels to NumPy dimensions so that we can reference specific dimensions of our raster using strings or names as opposed to indexes. So that's very analogous to what Pandas does for NumPy. So Pandas adds the ability to label NumPy arrays and refer to them as labels. And that's one of the key value propositions of Pandas. So Xarray does the same thing, but for raster data. And Xarray really, if we look at the Pandas panel, which was an attempt to have multi-dimensional, so not just rows and columns in Pandas data frames, we can see where Xarray came from because it's somewhat ND Pandas is what we can think of Xarray. And Xarray-Spatial then adds additional universal functions on top of that. So let's dig in a little bit more. So this is xarrayspatial.org, but moving over to the GitHub page where you can come and access all the code, we can go down and see a little bit of the ecosystem that this tool plays in and how it fits in. So in this graph here, we see Xarray-Spatial, and then we see the required dependencies in aqua or this green, and we see optional dependencies in yellow. So a lot of these dependencies here correspond to fill a niche within the geo stack. So we know that CuPy is going to be filling the GPU niche, while R-tree over here is an implementation or a wrapper around libspatial index for creating spatial indices. And then we have a couple of other dependencies here like Numba and Dask. It might be a little difficult for you guys to see that right there. Sorry, I just changed my size here. So we have Numba and Dask. So Numba would be our JIT compiler for making all of these functions fast. And then Dask represents the horizontal scaling of being able to run these analyses across a cluster or just across many processes. So this is a little look at the ecosystem around Xarray-Spatial. And digging in, we can see a couple of examples of maps that were created using Xarray-Spatial. So this port accessibility map has some proximity and some data shader in it. But the area to really get going here in Xarray-Spatial is to look at the examples. So I'm coming up to the source code. I'm going to make my screen a little smaller. I went a bit out of control there. So I go over to examples. And we're going to see that there's a user guide here. And this user guide has a bunch of topics. We're still filling it out. We still need to fill in 6 and 7. Some nice contributions there. But it starts to show the modules that are available within Xarray-Spatial and how you can use them, and how you could take one of these notebooks as a template for your own problem. So you could start with one of these notebooks and drop in your own data sets and see how far you can get just off of the user guide. So in looking at the user guide, I've downloaded Xarray-Spatial. I've cloned it from GitHub. I'm now running a Jupyter notebook, and I have a couple of the example notebooks running. So let's walk through these a little bit, and then we can see what Xarray-Spatial does. And folks are welcome to jump in with questions or comments as we go.
What's that stuff that is from like 6 years ago?
Oh, this is a Landsat image. So this is a 6-year-old Landsat. I believe it's of like Mobile, Alabama.
No way. That's awesome.
Yeah, go Mobile. I was actually just driving through there this weekend. So, in looking at these tools and understanding how we use these with our data, I'm starting with the surface tool notebook. So these are surface analysis tools, things like Hillshed, which is illuminating a surface using a light source at a given altitude and angle, slope, curvature, aspect, viewshed. These are other surface analysis tools which are named for geo professionals, right? So as we may do this similar things, but depending on the domain that you're in, it could be called something different. So within geo, we refer to the first derivative as slope. Within NumPy, they may refer to that as np.gradient. So there can be an impedance mismatch between disciplines, and Xarray-Spatial's focus is to meet geo professionals where they're at and provide them with spellings for these functions that they're somewhat familiar with. So curvature in geo is the second derivative, like acceleration. So looking at specific slopes and understanding, being able to pull out other features from an elevation model. Aspect is the direction of the slope, and viewshed is all about line of sight. So looking through, and I'm just going to start executing some of these cells here using return and shift. And the first thing that you need to do in exploring any library is have some data to work on. Fortunately, Xarray-Spatial includes a Perlin noise function within generate terrain, and it takes a data shader canvas. If folks aren't familiar with data shader, just a brief pitch on data shader. So data shader is a general purpose rasterization pipeline, not specifically geo, but allows you to go through a clear series of steps to reveal structure in your data and deal with problems like overplotting and oversaturation and undersaturation. In this example, what we're doing is we're instantiating a canvas with a height and width and an X range, Y range that's somewhat equivalent to the Mercator coordinate system. I'm passing that canvas to generate terrain so I can generate some data to work with. And then I'm using data shader's shade function to actually color map this array from black to white using a linear stretch of the colors. So there's a fairly tight integration between Xarray-Spatial and data shader, in that we need data shader to get us into raster format. We might be starting with vectors. So in the geo world, another collision of terms, vectors refer to discrete representations, points, lines, and polygons, tri-meshes and quad meshes. Those are all vector types. And we, in the raster world, where we're dealing with regularly gridded data that has a origin and a resolution and extent, we need a way to convert between the two, and data shader is the vector to raster solution that we're using right now. And data shader will also handle things like raster to raster conversion, which we call resampling. So being able to do upsampling and downsampling of existing rasters. allows us to co-register grids. So this canvas acts as an object to co-register arrays.
So maybe a dumb question here. So a raster is just a multi-dimensional array that's the uniformly to grid, like that's basically a uniform. Is that it?
Yeah, exactly. So like we're all fairly familiar with raster formats, things like PNGs, JPEGs, TIFFs. Those are all raster formats. Mm-hmm. We use that term raster in the geo world, but in in the physics world, we may use ND array or something as opposed, or in the NumPy world. Just really a semantic difference there. So yeah, in our case, the rasters are represented usually by 2D NumPy arrays, but they certainly can be 3D or 4D also, depending on what we're looking at and if there's a time component or if there are different layers for the same area that we want to explore. We can many times pack those into 3D arrays. But for our purposes here, we're just thinking of 2D NumPy arrays. In this case, we have like a 600 by 800 NumPy array with its height and width. And but what we're not doing in Xarray-Spatial is the color mapping. So Xarray-Spatial starts and ends with Xarray data arrays, and to do color mapping or vectorization, rasterization, the vector to raster conversion, we would be using data shader. So this is some Perlin noise representing some elevation, so that we can explore the Xarray-Spatial functions. Apply a terrain map, a terrain color map, and we can come down to one of our first analysis functions here, which is hill shade, so illuminating a terrain. And the syntax within Xarray-Spatial is we're going to import the function we care about, and then pass a Xarray data array to that function and get a new array back. Right now, we're then shading that array from gray to white with 100% opacity at 255 and a linear stretch. And we can start combining arrays together to make nice cartographic outputs. And you can judge whether this is nice or not, but you can stack these outputs just using the data shader stack function. So here I have a terrain layer, and then I have an illuminated version of that. And I'm composing them together by changing the alpha on the terrain so that we can get some shadows on the terrain that we're working with. And that's the hill shade function there. Now slope is going to calculate the slope of the terrain in either degrees or in percent. And you can imagine how once you've calculated the slope, you could use all of your normal logic within NumPy or within Xarray to then filter or threshold that data. So in this case, we're having an imaginary avalanche risk, and we're highlighting those areas where we're between 25 and 50 degree slope, so that we can highlight in red here risky, and that might be difficult to resolve through the screen share, but we can highlight risky areas that might be predisposed to avalanche. Curvature, kind of similar thing with a different functionality. Just to, in the interest of time, I'm just going to keep this moving, but there's a lot of these functions in here that are classic raster spatial analysis functions. So Viewshed, we've implemented our own Viewshed, which is all numba-ized, so it's very fast. And the idea behind Viewshed is that we have an observer, and what we want to do is we want to see all of the pixels that are in direct line of sight of that observer. In this case, we have what is somewhat of a hill or just a normal distribution in the middle of the image. And we want to calculate a viewshed and see which pixels do we see and which ones are obscured by through line of sight. So what we do is we import Viewshed. In like all Xarray-Spatial functions, we're going to pass in an Xarray data array. In this case, we're also going to specify an observer location. And then we can highlight all of the pixels where we have direct line of sight from this observer here. And the output array is actually the angle to the other pixel. So you can see there's a little more red. The red is a little darker here because the actual values that come out of Viewshed help you understand what the angle is to that from this visible pixel to the observer. And that observer can be also have a height, and the target can have a height. So imagine that I'm about 6 feet tall. I need to keep that in mind as I calculate my line of sight. So that would be observer height. But then also I might be trying to see things that are maybe 30 meters above, and now I'm mixing measurement systems, but let's just say I'm trying to see something that's 20 feet above the ground, then we can specify that as a target height. So this is Viewshed.
And by the way, Brendan is not 6 feet tall.
Yeah. And not today, I'm sitting in this great chair, but so yeah, so if we combine this together and we look at our imaginary terrain that's been hill shaded and color mapped, we can place an observer on this terrain and then run Viewshed and pull back all of the pixels that would be visible to this user from this location. And so that's Viewshed. And if we look at the time, right? So if we look at the wall time of sub-second, that's a big thanks to the folks at Anaconda and the folks that contribute to Numba, because it's Numba that allows us to run these algorithms quickly and compile them to basically C order of magnitude speed. And hopefully I'll have some time to quickly pitch a little bit more of Numba and look at some source code of how we implement these functions. But so we're in the user guide, so you can download this user guide after you clone, well, you get it when you clone the Xarray-Spatial library. But another category of tools that are in here are proximity tools. And when we think about proximity, we think about 3 different types of proximity: distance, allocation, and direction. So in distance, we're looking for the output to be, and let's make this a little more concrete, but we'll see some examples here. I'm starting by getting some data. This is a pandas data frame with some XY locations and IDs. And then I'm rasterizing these points using data shader. So this would be the canvas.points. And I'm using a little Dyn spread just to make deal with undersaturation to resolve where these points actually are. And the proximity tool is going to take the Xarray data array as input, and then give an output array of the distance. So in this case, if we just call proximity, we're going to be getting distance back. So the blue colors here represent the distance to the nearest point. And you can start to make out some lines. And if you know the Voronoi diagram or the Voronoi diagram, as I say it, people correct me, but that's what happens when you learn stuff through reading, is you can start to make out some patterns here of distances to their closest point. So we can see regions which one point is more influential than another, just based off of pure distance. And so when we're thinking about proximity, right, we have distance, we have direction, we have allocation. Those are all metrics that we want to get out in our result grid. We're using great circle distance in this case, as opposed to like a Cartesian distance. And this works with any type of array. So here we've rasterized a line and we're doing distance to this line. So we get that, that Xarray data array back. And this is a key, proximity is a really key feature to pull out of spatial data, because it can be another dimension for your machine learning models. So when you're thinking about feature engineering, you may think about Xarray-Spatial as like, hey, I need to tease out some more orthogonal features about my data. So let's start looking at spatial information. How far is that point away from, say, another point or area of interest? That's something that Xarray-Spatial can help with. And we can also obviously threshold the result distance arrays. And here I'm just thresholding this array to pull out a narrow band around my line of interest. So this is all distance, where the result that we get back are distance values in the coordinate system of the input array. So if we input an array whose dimensions are in meters, we're going to get back meters as the cell values in the distance matrix. But we also have allocation. So in allocation, what we want is we want to have the values of the output array be the ID of the object that's closest to, and this is the really, we're getting much closer to the Voronoi diagram here, where we can see that all of the pixels within this region are closest to this target point here. And then the last type of proximity analysis would be direction, where we want the output values to be the bearing to the point of interest. And so we can see that not only which point these go to, but the direction to the closest point. So there's a little bit about proximity tools. There's right now we support Manhattan distance, just regular Cartesian distance, and great circle distance, but certainly easy to add additional distance algorithms if folks want them, and might be a fun place to contribute. I think we have one issue right now for Mahalanobis distance. And what we may find in the future is that we want to get rid of our distance objects altogether and use something like SciPy's distance metrics and get a bunch of distance metrics all in one go. So a little bit about proximity. Zonal tools are particularly useful. I would say out of all of the tools inside of Xarray-Spatial, Zonal is one of the ones that's used the most. And they're used when we want to summarize array by some irregular vectors. So those might be points, lines, or polygons. And what we want to do, so here in this example, we have our classic Perlin noise island with our hillshade. It might be hard to see, but there's actually a line going across here. And that line has a few different segments. And in my mind, what this is that I'm planning a hike across this mythical terrain. And each one of these segments is corresponding to a different day in my hike. And what I want to know is some aspects of the terrain during that day. What is the range of terrain that I'm going to be hiking, and understand some summary statistics. And that would be based on using one segment of an array to summarize the underlying distance raster, or sorry, height raster or elevation raster here. So in each day we have a separate segment. Excuse me, and that's where zonal statistics and zonal tools would help. So here we're passing, we're setting up a zonal stats function that takes two arguments. It takes a zone aggregate, and this zone array or aggregate, a lot of different names here, represents the areas that to summarize. There are hike segments for each day. And then the terrain is, or value raster is the values that we're going to summarize by our hike segments. So we've associated an ID with each segment. And then we're getting some summary stats about that day. And we can see the min and max elevation for the day, and the standard deviation, and the variance. And that might help inform us, what we need to bring on our hike. But unlike other zonal statistics tools, we allow you to create any arbitrary Python function to apply in your zone. So in this case, I'm defining a Python lambda function here. And what Xarray-Spatial does is it injects the pixels only for that zone. And then you can refer to them on how to do the math to get your output. And the key of the dictionary becomes the name of the output. So I've defined a custom function here, which is just a range, and range is, I think is in there, but this is just for an example. This could be any arbitrary function containing any arbitrary third-party Python library. So anything that you want to do with each one of those zones, you have access to through this custom stats hook. So these are the zonal tools. There's also focal tools. So focal tools, convolution is like one of the classic focal tools, or a mean filter, where what we do is we're looking at a neighborhood around a specific pixel, and we're calculating some value and writing that value to the output raster. We support various different types of kernels. So as we think about kernels, they're the shape of the filter that is going across each pixel. We have our classic elevation. And we can see some syntax and style for creating convolution filters. We're calculating a cell size, and we're also using different shaped filters. There's a lot you can do with these. We still are building out this notebook more, But one tool that's inside of Xarray-Spatial, which is somewhat experimental, but is in there in Focal, would be hotspot analysis. So in hotspot analysis, what we're doing is that we're using a filter to go across the image and compare the stats within the focal area to the stats of the global raster to try to find statistically significant hotspots. So that's some work that we're continuing to do to build out the focal module. But Focal happens to be one of the ones that's easier to run on GPUs. And so we have pretty decent GPU support for the Focal module already. And getting towards the end here, but classification tools, when we look at 1D classification, we can take our elevation, and here we're applying a quantile binning method of 15 different bins of our elevation, and we can start to see it discretized here into different areas. And also classic equal interval classification, and natural breaks or jenks, which is just 1D k-means more or less, that allows you to classify elevation into 15 different groups. And also regions, which are going to highlight based on pixel connectivity. So where we don't want to group based on the bins of the values, but want to bin based on the adjacency of the values. So these are regions are going to define all the separate regions inside of the raster. So there's additional pharmacy desert notebook here, which is a good real world example of how to use these tools for a problem. We were specifically looking at census block groups, which have particularly high populations of senior citizens, which are also very far away from deserts and don't have access, very far away from pharmacies and don't have access to those services and are thus in pharmacy deserts. So this notebook here, which is in the Xarray-Spatial GitHub, would show you an example analysis of using zonal stats and classification all together to come up with the top 10 pharmacy desert counties of the United States, #1, which is Hooker, Nebraska. And when we have our final output here highlighting those counties. This is all scales with Dask. So not all of the tools are Dask enabled, but that's something that over the next 3 to 6 months, we're going to be specifically focusing on and making sure that everything runs on Dask. And everything is fast because of Numba. So anytime anything fast works in Xarray-Spatial, it's because the Numba team provided us with a way to express our analysis in a fast way. And just back to kind of wrapping things up here, this is the MakePath blog. You can find a lot of our activities and highlighting new developments in the open source front that we're doing. And so thank you guys so much for having me here. I just wanted to finish out just by showing one thing, which is pointing you guys at the first file if you want to really dig into the code here. The first file that you should look at is the slope implementation. So if you look at the implementation of slope, which most folks understand pretty intuitively what slope is doing, you can see how we implement it for CPUs using Numba, how we implement it for Dask using Dask map overlap, right? We can see how we're implementing slope for GPUs using the CUDA.JIT decorator. And we can see how we sew it all together into a public API, which is the slope function. So in this slope function, we have our 4 cases that we're interested in supporting: the vanilla NumPy array, the CuPy array, the Dask CuPy, and the Dask NumPy. So a good place to start in really digging into the code would be looking over this slope.py file. But thank you guys so much, and happy to take any questions. And looking forward to the world opening back up and coming to visit DC and see you guys in person.
Okay, thank you so much, Brendan. Any questions from the group?
I have a small one. Hi, Brendan. Thank you so much. Can you repeat what a raster is? What's the relationship between an array and a raster again?
Yeah, so a raster is just a regular grid, a lot like an array, but it's the name that we use in the geo world. So there's a discipline issue here, right? It's not that you don't know what a raster is, it's just that we call it something different. So a raster is synonymous with an image or, you know, and we tend to represent images in arrays. And so they're pretty synonymous.
Awesome, thanks.
Brendan, I am curious about like how was it how was the community just support as you were like open sourcing this stuff and like building it out, and then also like how did you sort of drive your first few set of features for this project?
Yeah, that's a great question. So it's been a little bit of a long haul. I really started thinking about a lot of these features in 2016. And then I created a library, which is not known by anyone, that's called NGO. And NGO was an attempt at doing polygon rasterization for Datashader. And it got beat out by Spatial Pandas, which is an awesome library from John Meese. So I ended up with my own sparse vector representation and my own rasterization code and a bunch of functions on top of it, but nowhere to plug it in. So what we did was we threw away the rasterization code and we just kept the these universal functions and put out Xarray-Spatial. So it's actually been sitting, or a lot of this stuff has been in my mind for a while, and then was implemented inside of Datashader and moved out into Xarray-Spatial, or was part of NGO and then ended up becoming Xarray-Spatial after the polygon rasterization case went away. And Spatial Pandas is a really great library. Also, if you're doing polygon rasterization in Datashader, that's the dependency that it uses.
That's awesome. Any other questions before we officially call this a meetup? All right. Well, thank you everyone who joined us. Please look for our next meetup. I believe that is Blazing SQL. And we're going to learn a lot about SQL and GPUs. All right. Thank you very much.
Great. Thank you, guys.